I'm confused by the whole notion of analog verification. I mean, we all have nice organized methods for verifying digital stuff, but with analog, even the design part seems like a bunch of magic. You wave your wand over your hat, engineering propeller beanie, and say some hocus pocus about capacitance and voltage swing, and poof! You might get a rabbit, or some birds, or maybe even an LLC resonant half-bridge converter. Magic! But not verifiable. Hi, I'm Amelia Dalton, host of Chalk Talk, and I want to get to the bottom of this analog magic mystery. Today, my guest is Mass Sivilotti from Mentor, and we're going to talk about analog verification with Tanner Designer. You know what? It turns out it isn't magic after all. Before we get started, don't forget to click that link. There you can find out more information about analog verification with Tanner Designer from Mentor. And before we go, you didn't forget to click that link, did you? There you can find out even more information about analog verification with Tanner Designer from Mentor. Hi, Mass. Thank you so much for joining me today.
My pleasure.
So, most of my verification experience has been with digital parts of my design, and I think a lot of engineers are a little confused about analog verification. So, Mass, just what is analog verification?
Well, there are several parts to analog verification, and because the components are a little bit more complicated than perhaps some of the digital components are, the specification part is very challenging. So this is a traditional V diagram where you have a refinement of specifications. Then you actually do the design work at the bottom, and then you test against those specifications. But there are really four parts to the process. You first have to agree on specifications. And this is very difficult because sometimes the interface to the validation flow, right? Verification is guaranteeing that you built what you intended to build. Right. Validation is guaranteeing that you built the right thing.
Yeah.
That needs to be captured. Sometimes that's done informally, but what we're trying to do here is formalize that. Secondly, you have an assessment component. This is what people traditionally understand. You do experiments, you do simulations or tests.
Okay.
And you simulate over parameters, voltages, and temperatures. You simulate over corners. You do Monte Carlo simulation to take all kinds of process variation into account. And you create these things you call tests, and you may have an awful lot of them, so you have to manage them.
Sure.
Recently, there's been a new emphasis on more formal process when it comes to verification. ISO 26262 is important in the automotive world. DO 254 has been around for quite a few years in the government world. But even if you don't have a formal process, you would like to have at least an informal process so that there is at least a reduced likelihood of mistakes being made, or as I like to say, no place to hide.
Right.
Things get found out, and they get found out in a timely fashion where you can still do something about it, not after you've committed to fab.
Right.
And the third area is one of sort of regression testing. There are lots of things that change over time. Processes change, PDKs change, tools change, and you want to make sure that the new tools, the new process, the new PDK still works the same way that you thought it did. And the fourth area, and this is sort of an important area for what we're going to talk about later, is communication. You need to both communicate up to management and also communicate within a team and communicate externally to customers with things like data sheets.
Okay, so Mass, what is the typical order of steps that we do for verifying analog?
Well, traditionally, it's pretty simple. There's a design and simulation phase, and then there's what we call an aggregation phase. You bring together all these simulation results, and then you present the results. But it doesn't have to be a linear sequence. You can start, and what we've designed is a system where you can start pretty much anywhere.
Huh, okay.
And we call this sort of a virtuous cycle because you can begin with the simulation, or you can begin with the template for the data sheet, or you can begin with even non-simulation data, measurements on reference chip or a reference design or something.
Okay.
And you can have many different kinds of presentations. You can have, as I said earlier, presentations for internal reporting for status of the project, or you can report the results, again, internally in a design review or externally in a data sheet. You can use the results to drive more simulations, new simulations. So it's not just, let me do a whole bunch of simulations and then let me distill them.
Yeah.
And finally, and this is very important, you can reuse this framework across subsequent designs. So if you have a product family that has a lot of different variants, you're not starting from ground zero every time.
Right. Okay, so you said that traditionally this process is sequential. Let's start with explaining that as a baseline.
Okay, so a traditional design, at its most basic, is these steps. You start with a spec, and for the moment, we'll ignore where the spec comes from. We'll just assume that it's given to us.
Okay.
And then the engineer would say, well, okay, I need a test plan. And he may or may not formalize it at that point, but he needs to know what he's going to measure and how he's going to define success, right?
Sure.
Then perhaps an engineering manager, or if it's an individual engineer, he's going to prioritize the work and figure out who's going to do what and when they're going to do it. Then you're going to actually do the work.
Yeah.
You're going to do the design. You're going to do the simulation.
Right.
And this little step, of course, takes a tremendous amount of time and brain power, but we're gonna minimize it to one step in the process.
Okay.
Then the fun stuff begins, because now you want to try to integrate the results into your test plan.
Mm-hmm.
And you may want to repeat the test over and over again to make sure that things haven't changed.
Right.
And then you have to decide and figure out how to report the work.
Yeah.
And it turns out that those last three things can be very time consuming, and you can wind up having to sort of reinvent the wheel over and over again.
Yeah. So, Mass, that seems pretty straightforward, but what are these opportunities you talked about for improving that sequential process?
Sure. The design process, because people really can only do one thing at a time.
Yes.
they wind up having to divide and conquer.
Yeah.
And so I have a cartoon of a very simple component here on the left, an analog to digital converter. It's broken down from the system level to several blocks and individual cells. The design work happens at the cell level.
Yeah.
And you push down specifications down to the cell level. And then you design the components at the cell level sequentially, which is to say one at a time.
Sure.
So there's initially a need to do the partitioning and to capture the specs. Then when you put the whole thing together, you have to do more tests, more simulations, and you have to check your work as you go along to make sure that everything is working as you intend.
Yeah.
But in the process, because design is iterative, what you thought was perhaps the system as it was initially spec'd may change over time.
Yeah.
So you really have to, as I say, come back later and check your work, because there may be new tests that have been added. There may be new dependencies, and I've drawn one there on the left where some engineer decided he could reuse a component to serve two functions. But if you designed it to do one and then you change it to do the other, you have to go back and make sure that you are still within spec on your first function.
Absolutely.
And then there are external inputs, which people sometimes ignore, that may have changed over time. And here I use an example of a Foundry PDK model, the SPICE device models, or the simulation engine, or something may have changed. And you want to be able to come back and confirm that your system is still operating the way you intend.
Okay, so is this really an individual problem or more of a team issue?
It's both. And I have cartoons that illustrate this process just to make it very clear.
Excellent.
An individual designer starts with specifications and with a lot of sweat and toil and brain power creates a design. And with a lot of simulations assesses whether that design is within spec. And that process is both one of simulation and one of creating measurements that act on the simulation results.
Sure.
And this is a cycle. He goes round and round and round until the component works to his satisfaction. If you have a team, it's the same problem, except now you've got a whole bunch of folks working on a system.
Right.
And you've got some individual, typically a project manager, who has the responsibility for knowing or for deciding whether this design is ready to go to fab and worth the investment. And you have to communicate to that individual the actual status of the design and the fact that it does work to the level that he expects it to operate.
Okay, so I think I've got the basic picture. Now, tell me how Mentor's solutions play into this scenario.
Yeah, let's get concrete now. So we have this new product. It's called Tanner Designer. Its first and foremost goal is to manage the entire universe of simulations that correspond to a project.
Okay.
This can be a very large number of simulations. For a reasonably small IC, it can be thousands. We have customers that are doing tens of thousands of simulations on one project.
Yeah.
You have to report the results on each simulation. That's the pass-fail, if you will.
Yeah.
You have to report the status of the simulation, because sometimes simulations get interrupted or fail for no reason, or external factors. You want to track when simulations are last run, because some simulations are far more expensive than others, and you can't just start them up and every day. You may want to only be able to do that once a week because it takes several days to complete. And you need to rerun the simulations. You then collect all the results from these simulations, and you want to present them in a very user-customizable way.
Nice, yes.
There are lots of operations you can do, but the very simplest is to compare them against a reference. That's the typical, am I within spec, pass, fail.
Sure.
We use Microsoft Excel for the analysis of the data, for graphing, reporting, for generation of publication-ready documents like datasheets.
Yeah.
The user gets to specify the criteria for individual test pass-fail, so they can be as complicated or as simple as they wish.
Cool, okay.
The target audience, as we've mentioned earlier, is both individual designers tracking their own design efforts, engineering managers tracking multiple designers, but also documentation engineers and regression testers. And this entire process is what we call analog verification.
Very cool. Okay, so what all can I do with this solution?
Well, let's take a simple example here. This is a datasheet that is created directly from the tool.
Cool.
We have presentation quality graphics with no programming required on the part of the individual who assembled this.
Nice.
In fact, this datasheet actually took about 2 hours to do both the simulations and the creation for this example.
That's excellent.
It integrates with existing tools, Microsoft Office, email, and so on and so forth. All the graphics are high-res and, like I said, presentation quality. It's a single-click solution. You just push a button and out pops this whole thing. And again, if you have a number of devices or a number of components that are similar, and they're in a family, and so the same set of measurements and tests and so forth apply to them, it's very easy to reuse the template and extract, for example, the different schematics or the different charts that are created by the charting program and insert them into the datasheet.
All right, so Mass, can you give me an overview of the environment? What does my UI look like?
UI is very simple. It has an application that is shown on the left of this slide here. This application performs the 3 functions of aggregating the data, running and rerunning simulations, and viewing the results.
Okay.
The aggregation finds all the simulations that are located within a directory tree and collects all the measurements from all the simulations, and it tracks them. So there you see on the left, those are the individual simulations. They each have results, and I've shown one with a pass, one with a fail, and one with a unknown status. You can tell whether they are up to date, in other words, whether they've been run with the frequency that you told the tool that it needs to run them, and the status, whether they completed or failed to run the simulation itself, not failed specs. This is a report control that is sortable and filterable and hierarchical. You can add your own user columns. You can get those user columns out of the simulations, and I'll show you how to do that.
Cool.
And then there's a log window at the bottom where once the measurements are updating the Excel worksheet, if there are any issues, if there's any errors, they appear as hot links there that help you debug any errors in your worksheet. So for example, there we have an intentional error that we asked for a measurement that doesn't exist. If you click on that hot link, it will open up the spreadsheet and show you exactly where you made that request. For people who've debugged Excel spreadsheets, they know how complicated you can build these things, so it's nice to have debugging tools. Second thing you can do is run or rerun simulations, and you can choose groups of simulations. They can be either individual simulations or categories, like all the failed ones or all the ones that are out of date. And these launch the simulator on the net list that's created from the schematic that captures the test.
Okay.
And the final thing you can do is you can view the results. You can either report, well, you always report the results in the GUI, which is the pass-fail, but you can also launch our schematic editor on a test bench. You can launch a waveform viewer, and you can view the net list in T-Spice. So as you have hundreds or thousands, perhaps, of tests, you don't need to remember where they're all located on the disk. You can just choose the test here and click on the button.
Nice.
And it will navigate you to it. It's kind of a design manager in some sense.
Cool. Okay, so you also mentioned that I could report out in a spreadsheet?
Absolutely. The actual user-facing report is intended to be this Excel spreadsheet.
Okay.
And this contains the measurements from all those simulations that we aggregated. So we have a very simple query language where you can say, insert here the value of perhaps a power measurement as an example.
Okay.
And it will put it in this cell in the spreadsheet. And there's no programming required here. It's just a text query, and it's very, very simple. It's literally, it's the measurement name.
Right.
Then you can use that data in formulas that you write. So we have templates that we distribute, for example, that do simple pass-fail measurements within a range. So here's an example of a dozen or so measurements, most of which were within the acceptable range, and 2 of them are not. But all the coloring, all the calculation, all of that is done with Excel. You can also aggregate waveforms and other graphics. You saw in the earlier example how we had schematic diagrams and waveforms. Those can all get pulled in the same way that both scalar and vector measurement can be imported.
Excellent.
Here's a little bit more detail on how that is actually done.
Okay.
This is an Excel spreadsheet where the user would make individual queries for particular measurements. Here we have a simple ring oscillator. The oscillator frequency is a function of the load capacitance, and the measurement is called ring freak, and you just type it into a column in the Excel spreadsheet. It's that gray column, which you then hide because you don't need to show all of the annotation.
Right.
And it will populate the cells immediately to the right of that cell with the values. And this is a vector because this is a sweep over a load capacitor. So the second measurement is actually the load capacitor. And then what we show here is how you just use Excel to create a chart directly in Excel that plots that data.
Nice. Okay. So how do I know if my design passes? Is there a big green light?
Yes, there is. The pass and fail is shown back in the GUI, and that is calculated in multiple ways. It's taken from the result reporting worksheet. For example, in the previous slide at the bottom, we had calculated that all the tests pass, and we used that. So that would have been no, it didn't pass because 2 out of the, whatever there were, 15 measurements failed.
Right.
But you can also use individual measurements. So if you have a measurement in your Spice deck that is written to say, I'm within spec, you can use that directly as a pass-fail. We can also add a user programmable column. So any columns that come out of the spreadsheet can be brought back into the GUI. And all of these things can be used to determine the results.
Ah, okay.
So it's as simple as you want or as complicated as you want, but the user has complete control over the determination of whether it was successful or not.
Okay, so for those already familiar with the tool, what's new in this latest release?
So there's 3 big features that are new in this new release. One is integration to our waveform viewer. So you can use the waveform viewer both to generate charts, which are then imported into the Excel spreadsheet, as you see on the slide. You can also use the waveform viewer as a post-processor for doing measurements. So the numbers that you see at the top there can be the result of a measurement from the waveform viewer.
Okay.
The third new feature is that we can also import data from pretty much any data source.
Nice.
There's a very simple programming layer in Tickle where if you can reformat your data to look like comma-separated values, we can import that and use that as a measurement. So this can be used as an interface to third-party simulators, to test equipment, to specs that are handed down through third-party or external systems or whatever.
Cool. Okay. So, Mass, there is always competition, right? How does Tanner Designer compare with some of the other options?
There is always competition. Tanner Designer was designed for the Tanner customers who are used to having easy to use, easy to own tools, easy to operate tools. One of the big differences is that Tanner Designer is used after all of the original design work is complete. So you do not have to change your design environment, your design flow. You're already doing your work in a familiar environment, which is a schematic capture. Once you have your tests, that's when you construct your test plan.
Gotcha.
And all you have to do there is just publish, which is to say export the files to a directory where Tanner Designer goes looking. And it's actually not a single directory, it's a hierarchical directory. You can put it anywhere in the subdirectories below. So it's very, very easy to implement. It's very easy to manage and maintain. If you have a new test, no problem, just add it to the existing directory. This is easy to operate in both the individual and the team environments. Some of our competitors, they begin with the test plan, and it's a different environment. And so you kind of have to know what you're looking for before you've started looking for it.
Right.
And sometimes the aggregation of individual tests across users can require programming. It can require the support of a CAD manager or a CAD staff. And certainly it takes a little bit of effort. And finally, and this is a big one, our competitors don't use the Windows platform. So programs like Microsoft Excel are not available to present data and calculate results.
Oh, okay.
We make it very easy for people who aren't experts in creating documents to create very attractive publication quality documents.
Nice. Okay. So, Mass, can you give me your main points real quick?
Sure. In summary, Tanner Designer is very easy to use. It's targeted to both designers and managers. It's very flexible. It manages huge numbers of simulations for a project with all the information that's tied to them. What it does at the end of the day, it collects and presents all of the simulation information in a user-defined format. It makes it easy to compare against a reference. It makes it easy to add your own formulas for analysis. It makes it easy to generate nice documents like spec sheets or data sheets. And all together, it brings the analog verification down into the realm of a manageable, repeatable process, so you can easily confirm that all your design goals are within spec because you're using familiar tools throughout the whole process, and you are ensured final project success.
That sounds good to me. All right, where should I send my audience for more information?
Well, there's a number of websites, and I think they're actually all linked from the first one, but there's a mentor website for Tanner Designer. There's videos, and of course, there's helpful account managers who are willing to talk to you at any time.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Mass.
You're very welcome. Thank you much for your time.
And before we go, you didn't forget to click that link, did you? There you can find out even more information about analog verification with Tanner Designer from Mentor. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of eejournal.com or check out YouTube, keyword EE Journal.